Hello. Today we will be discussing Physics 2211 Lab 4 Oscillations. This lab covers pretty much oscillation motion of a mass attached to a spring, and we will understand how the motion of this mass changes throughout its uh, period of motion. And pretty much we will determine this by comparing the predicted model with a GlowScript code and observed model using Tracker to determine how the change of energy in the system affects either its motion or if there is no change of energy in the system. And pretty much from the results, we can determine a little preview is that there is extremely similar graphs for the predicted versus observed motion. And in addition, with the predicted motion, we found that the system would not lose any energy as each interval, the total kinetic potential and gravitational potential of the gravitational potential and the spring potential would all equal zero. Some important concepts are the momentum principle, which we'll use to update the velocity and the position of the spring, the energy principle, which we'll use to determine how much total energy is in the system, and then the system equilibrium, which is pretty much if there's any outside net forces, if there is any work being done to the surroundings. So with this, we can determine our observed model. We have our system, the spring, earth, and mass. And then we have the surroundings, which are none, because we put everything in our system. And we know that there is air drag, but we're going to neglect it for this purpose of the lab. And pretty much with our tracker, we just update each position with each frame. And every frame is about 0.095 seconds. And using that information, we were then able to identify our initial position, start time, and final update, which will be used for in our experiment in our predicted model. Those will be our initial conditions, and then we also took the x and y position and put it into a spreadsheet that we then downloaded into a CSV file, which we would then put into our predicted model. So our predicted model, the initial conditions, is pretty much what we just had in the observed model. We update the initial mass, the change in the time step, and then include every time step that would be from 0 to 9.4 seconds, so we could then see a total graph with each number. Next, we have the predicted model, and pretty much we have some constants, which is just like gravity, like the spring constant, which we determine in the observed model, and then the relaxed length. And pretty much we have to then do is update our energy, update our position, and then we have, so pretty much the total energy is the K, the UG, US, and E. And then while we are in our loop, we then have to update the new position of L hat, and S. And then we also have to update our total energy, but we will see that each time we update the total energy, it's equal to zero. So pretty much we then have is our results. So what we were able to determine is that the predicted model and the observed model are similar. They consistently show the oscillations of the mass with slight deviations. As you can see, the y position is very similar, almost identical, while the x position seems that the uh, predicted model was a little bit further ahead of our experiment model. And now this could be one source of error is because we never gathered the same consistent middle point of our mass at each interval. And then our energy principle, we can see that the total energy of the system is zero when on the spring, gravitational, and kinetic energy, which shows that there's no work done on by the system. And although this is accurate, we do know that there are other forces at play that we neglect because we want to make sure that we can determine if the two systems are equal. So like drag force or rotational kinetic energy could explain these differences. Finally, we have what does it mean? So is the energy principle satisfied? Well, yes, the energy principle is satisfied because we see that the total energy is equal to zero, which means that the change of the energy of the system is equal to zero, which makes sense because we make sure that nothing else is outside of our system. Everything is inside our system. So the total energy would be equal to zero, or the change of the total energy would be equal to zero because there is no work done by the surroundings. And finally, we find our period of oscillation by taking the x and y position and determine at that same point later what is that time in. So like we can see, we take about the 1.2 second mark to like the 3.8 second mark and determine that The X position is like 1.615 seconds. Our Y position is 1.519 seconds. And the difference between them is about 0.096 seconds. Thank you.